So now let's not talk about anything inappropriate. Just the screen. All right, folks. Welcome to the. Here we go. So we talked about domain, and the domain. When we think about things that we can plug into sine and cosine, we are allowed to take the sine of anything and the cosine of anything. You can take the sine. You can take this. You can take the sine of 5. You can take the sine of. You can take the sine of any negative number, as well as cosine. Okay? However, if you notice, there are certain... The fact that you pointed this out to me is horrible.
I was like waiting for you to do it the other day.
So the question is, what are the... Hold on. So... Okay, back to it. The question is, what are the outcomes? When you plug in any particular number, what are the outcomes that you get? Okay? And the outcomes happen to be between -1 and 1. Yeah. Yep. They happen to be between -1 and 1, okay? If you go around the unit circle, the largest point that you can get is 1. However, the smallest point you can get is -1. Okay? -1. So, that's our range. Our input is anything we want. We can go as many times around the unit circle as we possibly want. Okay? Or backwards around the unit circle as many times as we possibly want. But sine, the outcome is going to be between -1 and 1. And cosine, the outcome is going to be between -1 and 1 as well. Okay? That's our range and our domain. The function f is periodic with period c if f is a function for which p is the smallest positive number such that f of x plus c equals f of x. So that's like saying the position that the terminal side is located has a similar position between 0 and 2 pi. And if you can get that to that similar position between 2 pi on the unit circle, then basically we can subtract 2 pi from anything that we want. Okay? We can subtract it or add it. We are going to say, hey, instead of being 2 times around, I'm going to subtract 2 pi's and go back to my original standard position. Okay? Or something like that. That's what that period is saying. Okay? So for instance, we have 7 pi over 2. 7 pi over 2 is, you can count the halves if you want. You have half pi, full pi, 3 over 2 pi, 2 pi, and then you keep going, right? So that's literally 6 pi over, that's 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2. So that is 1 full revolution all the way around, and it's right here. Okay? It's located at the lower quartile, in between the 2 lower quartiles. Okay? That is 7 pi over 2. So what we're saying is that has the same value as if I subtracted 2 pi. Okay? So I subtract 2 pi from that, and all of a sudden, we have it between 0 and 2 pi. And now we are back to the regular unit circle, rather than going in a whole full revolution around. So that's really handy, because that means I can give you any angle as big as possible that is currently within the multiples of something that is friendly, like over 2, over 3, over 4, okay, or over 6, and we can get a value for that, okay? Cosine and secant are even functions, and the other 4 are odd functions. That's completely random, okay? What does that mean? Well, do you remember how to discover if something... Oh, man. Do you remember how to discover if something's even or odd? You guys remember that? Okay, it turns out you can find out if something's even or odd by plugging in the negative x value. If you plug in negative x, what happens? Does it stay negative or does it go positive? If it goes positive, it's even. If it stays negative, it's odd. Okay? So, for instance, if you do cosine of negative t, we get positive t, cosine of positive t. Those two values are the same. You can look at this on the unit circle. Okay, if you look at the unit circle, and we look at, let's say, cosine of pi over 2, okay? So we have cosine, pi over 2, why not? Here's cosine of pi over 2. We end up getting this point, which is 0, 1. So the cosine of pi over 2 is 0, 1, okay? What is the cosine? Well, so that means cosine of pi over 2 is equal to the x value, 0. The truth is that if I do the negative cosine, it should also equal 0. So let's do that. If I do the negative cosine, which would be negative pi over 2, we have 0, negative 1. Which means that these are the same thing. The cosine of negative pi over 2 happens to equal 0 as well. They have the same value. Okay? And that's kind of true for cosine. Cosine does that. You can do it at a different spot. Maybe, how about pi over 4? Pi over 4, cosine of pi over 4 equals the square root 2 over 2. What about the negative cosine? Or the cosine of negative pi over 4? That's down here. Negative pi over 4, cosine of negative pi over 4 equals square root 2 over 2. So the sign doesn't change. That's the difference. If the sign changes, it's an odd function. If the sign doesn't change, it's an even function. They have the same value. Now what if I was to do the same thing with cosine? If I was to do the same thing with sine. If I was to do the same thing with sine, I have sine of pi over 4, that equals square root 2 over 2. But if I have sine of negative pi over 4, all of a sudden, my answer is negative square root 2 over 2. That indicates that sine is an odd function. Okay? It has different values. So there we go. Odd functions, sine negative t and negative sine of t. That's our value. That's what we get. The solution to sine of t is negative. Okay? Maybe I should have recorded this, like the video, but sorry guys. I wrote something on the board. Tough luck. But I hope the best for you. Go ahead. So secant does the same thing. So secant, if you do secant of a negative angle, it will give you a positive outcome. Cosecant doesn't. That follows the same pattern as sine. Plug in a negative angle, you get a negative outcome. Tangent does it, and cotangent also does it. Okay, we have 4 odd functions, and we have 2 even. And these are called even and odd functions, even and odd properties. Okay, even and odd properties. So, let's look at an example here of a period. Okay, so go ahead and flip the page. Good. Using the period to evaluate sine and cosine, we have these particular examples. Because 13 pi over 6 is equal to 2 pi plus pi over 6, that's 12 pi over 6 plus 1 pi over 6, then sine of 13 pi over 6 is equal to the sine of pi over 6. And the sine of pi over 6 is 1/2. We can just do the same thing with that period, okay? The same thing of what we add to it, okay? So the 2 pi goes away, and we can simply do sine of pi over 2 because it's in the same position on the unit circle. Cosine, same thing. Now look at this one. If I look at this one and I say, I don't know if I wrote this right, cosine of negative 7 pi over 2, that would be actually negative 4 pi. That should be a negative 4 pi. Okay? Sorry about that. Negative, right there. So that's a negative 4 pi plus pi over 2. Okay, that has the same position. Is that right? Why am I thinking something's off here? Think. Yes, that's the same spot. Okay? Because that would be 8 pi over 2, negative 8 pi over 2, plus pi over 2, that's negative 7 pi over 2. Okay, I was right. So, yeah, that's negative. That has the same position. So if you add or subtract that pi over 2, whether it's negative or positive, or that 2 pi, I mean, however many times, wherever it lands on the position that it's supposed to be, whatever you add to that to make it equal to what we have here, that is the position that we're already in. Okay? So think about this. If I take my unit circle, well, I have one kind of halfway written over here, and I go one full revolution around, that is negative 2 pi. Another revolution around is negative 4 pi, and I add pi over 2. I should be right here. Sorry, right here. Okay? Which is pi over 2. Cosine of pi over 2 is going to be 0. Cosine of pi over 2 is 0. I have that written down. Oh, wait a second. What's this? On your own, find cosine of 9 pi over 2 and sine of negative 7 pi over 3. Do it. Use your pencils and write things down on your paper about the period. Identify the period. If you can add or subtract it, you'll be good. The unit circle is on slide 2 or 3? Or page 2 or 3, is that right? Page 6. I'll get you guys all a unit circle next class. Probably gonna. Okay, good. Let's go ahead and write this as cosine of something pi plus our value. What can we basically take out of it?
4 pi.
You can take out 4 pi. 4 pi is 8 pi over 2. So 4 pi is coming out. And what's left over? Pi over 2. And if that's true, then cosine of pi over 2, oh, that's 0. That's this one right here. Okay? Interesting.
Why do you just do pi over 2 and not 4 pi?
Well, if this is saying the location of 9 pi over 2 is right here. That's where it's at. So we're saying, hey, why don't we undo 2 revolutions and we'll just end up right here. Same spot. You get the same values. So if we undo those 2 revolutions, which is 4 pi, then we end up back in this specific location on the unit circle.
So you don't count the full revolutions?
No, it's 2 revolutions because it's 2 pi revolution. 2 pi is 1 revolution.
Full revolutions. Like,
Oh, it doesn't. It's the same value. So like, here, let me. So this is one full revolution is like this. A second revolution is like this, and we end up with this position right here. That position is the same thing as pi over 2. Okay? You'll get the same values. And in reality, it's like, I mean, I hate to do this, but I will. It looks like this. 1 revolution, 2 revolutions, back to here. So it's the same value. Okay? So we subtract those 2 revolutions, and we end up getting just pi over 2. How about sine of negative 7 pi over 3? That one's a little bit harder. Did anybody figure out how to get negative 7 pi over 3 on the unit circle by adding or subtracting a period? To get it on the positive unit circle. That's between, just to clarify, that's between, I'll say theta is between 0 and 2 pi. That's something, that's like a restriction of the unit circle. Okay? If I ask for something in between that value, I'm saying I want it in the unit circle. What do you think? Yeah?
Would it be negative 3 pi plus 2 pi over 3?
Negative 3 pi is not allowed. It has to be either 4 pi or 2 pi. What do you think?
4 pi.
4 pi? Okay. So that's 4 pi. So this is saying, here's a visual of that. So this is to help some people out. I am going around 1 pi. So that's 6 pi over 3, 7 pi over 3. That's where I'm located right here. You can kind of see it. You can kind of tell it's negative pi over 6. But we got to get somewhere, yeah?
Okay, so I have a question. So, you know how it's like 4 pi plus pi over 2? Like, can that be like minus? Or does it always have to be like...
Like minus?
Could it be like a negative? Or does it always have to be like an addition sign?
If you have it in this form, you could do it. Pi over 2 minus something.
Okay.
But you can't have a negative value over here. It's not pi over 2, though. So you're saying, I'm going to take this and I'm going to go 1 revolution all the way around. I'm going to go 2 revolutions all the way around. Okay? And then I have to figure out, how do I get to this location right here? Okay? So you would say, well, what is it? Well, let's think about this. Instead of doing it the complex way, which is the way I'm doing it, just take 4 pi and subtract 7 pi over 3. If you do that, you get 12 pi over 3 minus 7 pi over 3. And what value do you get? 5 pi over 3. So we are going to take that value and say it's plus 5 pi over 3. And that will get you negative 7 pi over 3. Now, here's the thing about this. All you have to do is recognize the period and the difference of that period with the terminal line. So that's like saying, hey, that's 7 pi over 3. If I just subtract those, I get my value. Where is 5 pi over 3 on the unit circle? It actually is right here, which is what I want. Yeah?
So I'm just confused like how you got the period the negative 4 pi.
Negative 4 pi.
Yeah, and like how like from that question like how you now that you have to find that.
Well, I can't add a negative number to it. Okay? That's a key thing. I have to add a positive number. So maybe we'll do another one. Let's do like, I don't know, sine, you haven't even answered any of this question yet. Let me just finish this question. Sine of 5 pi over 3, that is, it's negative square root 3 over 2. Okay? So this is, it sounds all complicated and stuff, but so if it's a positive number that's big, those are usually pretty easy. Okay? Those are usually pretty easy. So if I give you something like sine of, I don't know, 12 pi over 4, you should be able to figure that out. Okay? That's not reduced. Hold on. Let's try another one. So 13 pi over 4. How about 13 pi over 4? So 1 revolution is going to be 8 over 4. So that's 1 full revolution around. So what we're going to do is we're just going to say, hey, this is the same thing as 13 pi over 4 minus a full revolution. 8 pi over 4. And this is what you're going to be looking for. If you do that every time, you'll be fine. Sometimes it's 2 revolutions, sometimes it's 3 revolutions. So this turns out to be 5 pi over 4, and you can find 5 pi over 4 on the unit circle. Is there more of these? No, but I do have more space. I'm going to do more of these. Let's do some more. Now, here's the thing. After you get this number, forget about it. You forget about what you had before. Okay? These two have the same values. So this is going to be 1, 2, 3, 4, 5. It's going to be negative square root 2 over 2. Yeah?
How do you know if you're supposed to do just like 1 revolution or like 2 or 3?
It has to be however many it takes to get to the unit circle. Okay? So let's do one that's kind of weird. Let's do a weird one. Cosine of, let's do 28 pi over 3, not divisible by 3. Okay? There's a big number, but it's positive. Positives are nice because you just got to subtract the periods until you get to the very end. 28 pi over 3. Well, let's start subtracting the period. Let's subtract 1 period. That is 6 pi over 3. Well, that's not going to do it. How about 12 pi over 3? Well, that's not going to do it. Another 6. How about 18 pi over 3? That's not going to do it. How about 21 pi over 3? That's 7 pi over 3. Still not going to do it. How about 27 pi over 3? Now, all I'm doing is I'm saying how many revolutions it takes to get this thing between 0 and 2 pi, or 0 and 6 pi over 3. Same thing. These are the same things. So I'm doing multiples of 6 pi over 3. 6, 12, 18, 24. No. Whoops, did I screw that up? 6, 12, 18, 24. Oops, that's supposed to be 24. Sorry, screwed that one up. Multiples of 6. And you end up with 4 pi over 3. How many times did that go into it? Well, 6, 12, 18, 24, 4 times. So this is like saying 20. It's like saying 4 pi. No, I'm sorry. This is like saying 8 pi plus 4 pi over 3. We ignore the 8 pi, and we just do 4 pi over 3. Kind of makes sense?
Can we do a negative one?
Yeah, negative ones are a little bit weirder. So let's do cosine. I didn't even do the answer though. So 1, 2, 3, 4, negative. I think it's negative 1/2. Is that right? Good. Negative 1/2. Cosine of that is negative 1/2. Okay, one more. Sine a big one. Let's do a big one. 30 pi over 4. Negative 30 pi over 4. Okay? Cool. So we got to figure out how to get this back into standard unit circle position. Okay? How do we get that back to standard unit circle position? It's basically done this. It's gone 1, 2, 3. It's like way out there. Okay, 8. Well, actually, let's think about this. 2 pi. We're trying to get this between 0 and 2 pi, and we have 0 and 8 pi over 4 as our goal. Between 0 and 8 pi over 4. So let's start adding 8 pi over 4 to this thing until it turns positive. And that's all you got to do. Okay? Add 8 pi over 4. That turns into negative 22 pi over 4. Let's add another 8 pi over 4. Wait, this is like adding a bunch of 8 pi's over 4. That's all we're doing. Okay, add 8 pi over 4. That's another negative 14 pi over 4. Let's add another 8 pi over 4. That is negative 6 pi over 4. And then let's add one more pi over 4, 8 pi over 4, and we get 2 pi over 4 as our solution, which is pi over 2. Oh yeah, it reduces. Duh. Okay? How many did I do? Well, I did 1, 2, 3, 4. I did 4 times. This right here, this 30 pi minus 30 pi over 4, that's negative. That's the same thing as sine of negative 1, 2, 3, 4 revolutions. I happen to do 8 pi again. And then we add pi over 2. And that'll get us into this position right here. Same thing. Here's the thing. I'm not going to be worried about this. I'm more worried about, can you find sine of that pi over 2? Sine of pi over 2 is however you get that to pi over 2, that's fine. You just got to add or subtract periods to get there. If it's a big number, you subtract periods. If it's a negative number, you add periods to get there. That's actually pretty straightforward, right?
How did you get the negative 8 pi?
That's how many revolutions I did. So I did 1 revolution, that's 8 pi over 4. That's the next, so that's 1. This is number 2. This is number 3. This is number 4. And so that represents 4 revolutions to get to the positive unit circle. Okay. Well, there was a problem here that I said skip. Where was it? It was right there. Do this later. Well, you can do it now because these are over a period away. So subtract the period because they're both positive numbers, or subtract 2 periods if necessary, and then you find cotangent of those values or secant of that value. Oh God. You could even do this. I will even allow this. If you don't put equals, but you put a little arrow, just write what that value is going to be after you subtract the period. After you subtract a full period, what's your value? Anybody? Pi over 2. Good job. You subtract 4 pi over 2. Cotangent of pi over 2. Here we are at pi over 2. This is 0, 1. So cotangent is x over y. 0 over 1. Which means my answer is 0. Now if it was tangent, we would be dividing by 0. Our answer would be undefined. What about secant? You got it, Bailey? Oh, sorry. What? Looks like it's maybe just 1 period away. Did you subtract 6 pi over 3? And then that turns into, arrow. Secant of 4 pi over 3. These would be common values I keep getting over and over again. Secant of 4 pi over 3 is the same thing as 1 over the x value. What is the x value at 4 pi over 3?
-1/2.
-1/2. So that is now over 1 So our value turns out to be -2. Flip it, and you're good.
Yeah, I started looking for lines.
Okay, good. Capiche? Got it? Yes? You got it? You guys all? Okay. Oh, whoops. Keep, yeah. Cool. So this was your homework. You should be able to answer all those questions now. Not page 300. Oh my gosh, it's still 300. What was it, 270? Okay. Whoops-a-dazzle. Sorry about that. Shoot. I kind of lied to you. I'm going to keep going. Okay? Well, let me think. If I give you 20 minutes of homework, that means I have 20 more minutes of lesson. I know, that took longer than I thought. I thought it was going to be like
You'd have 25 minutes of lesson.
25 minutes a lesson, yeah. That's not enough to do a whole lesson. We'll have to make a compromise. I'm going to give you an offer you can't refuse. What? You guys have never heard that? I'm going to give you an offer you can't refuse. It's from The Godfather.
I've watched the movie.
Yeah, I just got the album from my mom. So let's just not stall anymore, and let's see how far I need to go. Where are we? We were right here, and what? Okay, there we are. We need to get to.
What the heck is with your pies, dude?
We need to get 16 slides done. That's my goal. After those 16, the first 3 slides are review. So the first 4 slides are review. So technically, only 12 slides. Okay, I'm sorry. I'm just gonna keep going. You are.
We can't finish it.
Your compromise is we will finish this. Okay, and then you can ask all the questions you want at the end.
Are we gonna get the
Packet. Yeah. Here you go. These are really long packets, and I made a mistake, and I didn't print them out at the print shop, so they are in 4 quarters. So get your reading glasses out, because some of these are really tiny. You're welcome. Saving trees. 1 packet at a time. Yes. It's double-sided. It is 4 slides. It is 28 slides total. It is time for you to give one of these sunglasses as well. It's so sitting behind you. Okay. Hey, so we're getting there, and I want to allow some time to. I kind of want to get through this. So, dang, I really want to give you guys time to work on. Okay, whatever. So anyway, we have our basic trig stuff here, and we've already gone through this slide basically, but this is just referencing that sine is equal to opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, and then we have their reciprocals. That's this flipped. Cosine flipped is secant, and tangent flipped is cotangent. And then it tells you opposites of all of those particular things. A quick review. Don't forget that. Moving on. Now remember, these are all based on special right triangles, 30, 60, 90, and 45, 45, 90. They all have locations on the unit circle that you could fill these in. If you feel so, go ahead and do that on your own time. Okay? Make sure you get those figured out and going. Okay? Oh, you do have reading glasses. Cool.
So when do you know that like cosine at 30 is like losing the unit circle as far as like finding the x value? It's just the angle.
When do you do that?
Yeah.
Whenever you see nice even numbers like 30, 45, 60, 90, 120, anything divisible by 30, anything divisible by 60, anything divisible by 45.
But like cosine can mean like the x value, but it can also mean like the calculator of 30 degrees?
Oh, it's going to be very specific to say use a calculator or not. Okay? If it does not have a thing that says use a calculator, you do not use a calculator. Okay?
So if it doesn't say use the calculator, then cosine use the x and like the x.
Yeah.
or something.
If it does say use a calculator, it'll just give it to you in a decimal. But you have to be sure you're in radians or degrees, depending on what that is. Okay? Now, cosine of 30 is square root 3 over 2. Tangent of 30 is basically 1/2 over square root 3 over 2. Those things are going to be true all the time. But you can imagine that square root 3 over 2 is going to be some sort of specific number. Okay, it's basically 1.76 divided by 2. Okay, that's what you get. So, something to think about. Fill those in. Good stuff. Okay. Now, cofunctionality. So let's talk about cofunctionality here. Cofunctions of complementary angles are equal. Okay? If theta is an acute angle, then there is a cofunction to that. Okay? And we have these true for each one of these. Now, you're probably looking at this and you're going, what the devil does that mean? Well, let's do a little bit of discovery here. And we're going to draw a... Not that. What? Did it go away? Oh, interesting. We're going to draw a unit circle here. Okay? And we're going to pick an arbitrary angle that is called theta. There's our arbitrary angle theta. Now, what we're going to do here is we're going to take 2 pi and we're going to subtract theta. Okay? So suppose this was, I don't know, 1/2, and this was square root 3 over 2. Okay? Now, if we were to take 1/2 and subtract theta from it, wouldn't we get something that would be like this, where this is now theta? Okay? That turned out really bad. That's theta. If we subtract it from 1/2, stupid thing. Okay? That's where we would end up. So what happens when you have pi over 2 minus an angle, what happens is it turns into the cosine of theta. Okay? Now, you're like, wait a second, time out. Time out, that doesn't make any sense. How could it just magically turn into that? Well, I gotta write it bigger. We figured that sine, we're gonna do, I don't know, let's do freaking pi over 3. Pi over 6. Okay? Pi over 6 has a certain values associated with it. That is 1/2 and square root 3 over 2. That's basically what I was doing. And if we take 1/2 and subtract pi over 6 from it, that would be pi over 3. So the cofunction is pi over 3. It's actually right. That's theta here. This whole thing would be pi over 3. Pi over 3. And if we look at the values of pi over 3, we end up seeing that our x's and y's switch. Okay? It turns out our x turns into 1/2, and our y turns into square root 3 over 2.
That's if you add what to it?
That's if you take pi over 2 and you subtract the angle from it. Okay? It's basically telling you that the relationship between these two angles is one where they have the same values, the same x and y values, but they just flip-flop. The x turns into the y and y turns into the x. That's the cofunctionality. If I was to look at cosine, it gives me the sine value of that. If I look at tangent, tangent flips and turns into cotangent. Cotangent turns into tangent. Secant. Now, secant's a little funny. You do the same thing over here. It actually turns into cosecant. Still, it follows the pattern that I've laid out, but that's a little bit weird. Okay? It's like the flipped version of sine turns into the flipped version of cosine. And so on and so forth. That's sine. No, I'm sorry, secant of theta. Okay? So if you take 2 pi and you subtract it from any angle, you get the opposite version, basically, of that value. If it's sine, the opposite of sine we'll call cosine. Or, it's not opposite, but it's like, it's frenemy, right? It's just like enemy, but they're still friends. Okay, that's frenemy, right? Yeah, good. Okay, moving on. Now, these little things here, they might pop up too much. I'm not too concerned about them, about the knowledge base of this, but I am concerned about basic trigonometric identities. Now, this is where we get to the good stuff. These identities are awesome, and you've seen them before, except one. You haven't seen one of them. Okay, it's called the Pythagorean identity, but we're not quite there yet. We're getting there. We're almost there. Let's talk about the 6 reciprocal identities. The reciprocal identities basically say if I take sine, I can rewrite that as 1 over cosecant. And you may be thinking, what? 1 over, well look, what is cosecant? We already know that cosecant is 1 over sine. We knew that in the beginning. So if I have 1 over sine, I get sine. And so these are the reciprocal functions. These are what they equal. Cosecant equals 1 over sine. Sine equals 1 over cosecant. They go right back to where they're supposed to be. We have cosine. We have tangent. Okay? Now these ones are a little bit funny. Sometimes these are written differently as quotient functions. There are 2 quotient identities, and they're ones you've already seen. Tangent is equal to sine over cosine, and cotangent is equal to cosine over sine. This gets real theoretical, and it loses a little bit of practicality, but that's where we lead into analytics. So, everything kind of makes sense as far as these go? No? So the definition of cosecant is 1 over sine. And the definition of sine is the y value. Okay? But it's also equal to 1 over the y value. This is highly redundant, but it can be helpful if you have cosecant on the bottom. Now we're going to get to the point where we take sine and multiply it by cosecant and something happens. Things start changing by manipulating them through identities. Let's move on to the Pythagorean identity. Okay, these ones are pretty standard. They are just the flipped version of every single one. The Pythagorean identity states that we have an equation for a right triangle. Right triangle is a squared, b squared equals c squared. Right? A squared plus b squared equals c squared. That's Pythagorean's theorem. That is opposite squared plus adjacent squared equals hypotenuse squared. Now, the crazy thing about this is that there are certain things that eventually come about with these Pythagorean identities. I can show you the definition of them, but it takes a while to figure out where they come from. Okay? The basic understanding is that A is our sine of theta and B is our cosine of theta. Therefore, sine squared plus cosine squared equals 1. Down here it reminds you that sine squared is the same thing as sine theta squared. Those are the same thing, okay? Those are absolutely the same thing. And then this little thing reminds you that if we have 1 over cosine squared theta, that is the same thing as secant squared theta, okay? So we have sine squared plus cosine squared equals 1. Hypotenuse was 1 for the unit circle. And then we have tangent squared theta plus 1 equals secant squared theta. Okay? Now you may be wondering, where did that come from? Well, that's basically dividing everything by a value. Okay? If I divide everything here by cosine squared theta, boom, I get tangent squared theta plus 1 equals secant squared theta. Okay? They're all different properties. If I divide this by sine squared theta, and sine squared theta, which I'm allowed to do, because that's a property, that's sine squared theta, what happens is that we get 1 plus cotangent squared theta minus secant squared, or cosecant squared theta. These are all identities. What's going to come about is that these are fixed. You will get a list of these that you can use for certain information. A couple of things you could do. Couldn't I subtract tangent over? You could also get 1 equals secant squared theta minus tangent squared theta. What if I subtracted cotangent? Well, 1 equals cosecant squared theta minus cotangent squared theta. You will not be giving those, but you can see that they even each other out, turn into 1. That's kind of a big deal. We can do the same thing here, right? We also know that sine squared theta, that's equal to 1 minus cosine squared theta. What am I doing here? I'm just doing algebra, okay? I'm just doing a little bit of algebra. That's all I'm doing. If I'm just subtracting cosine over. What else could I do? I could go back to the beginning and subtract sine over. So cosine squared theta equals 1 minus sine squared theta. That's the information that we can get by changing those. Write those down because they're really helpful to start out. Okay? This is a good one, and this is a good one. Because you're going to find spots where you get cosine squared theta and you can't seem to evaluate anything. But if you just change it to 1 minus sine squared theta, things start looking up. So now, back from the unit circle. We'll eventually get to the point where we solve these, but back from the unit circle, we are stepping away from it, and we are now just looking at sine theta, cosine theta, cosecant theta, secant theta, tangent theta, and cotangent theta. That's all we're looking at. And 1. But give them a handout. Oh, I don't have a handout yet. Well, you can reference those pages. It's kind of like a handout. Okay, here is the handout. Oh, shoot, I was really planning on doing that. Okay, so these are the basic identities. Here we go. Example of applying an identity. This is not an example of applying the identity. Oh, kind of. Okay. So suppose, those are a little bit out of place, but that's okay. Suppose we get, okay, we're doing good on time. We're doing real good on time. We're on slide 8. We need to do 8 more. So let theta be an acute angle such that sine of theta equals 0.9. Find the exact value of cosine of theta. Okay? So let's do that. What? I already did. Check it out. What we're going to do is we're going to apply Pythagorean's identity, and we are going to plug in 0.9 squared. Now 0.9 squared is 0.9 times 0.9, which is 0.81. And now we're going to take that and we are going to subtract it on both sides. And we're super close, right? We are at cosine squared theta equals 0.19. Now here's the thing that I don't think I wrote. That is cosine squared theta Remember, it equals cosine theta squared. Okay? Those are the same thing. So what I'm going to do is I'm going to square root both of those sides. Now I usually would do the plus or minus square root, but look at the instructions. Theta is an acute angle. What quadrant is that in? The first quadrant. And the first quadrant has two positive numbers. So we're only going to worry about the positives. So there we go. We get cosine of theta equals the square root of 0.19. Now, if you ever have decimals like this, you could always convert them over 100. And that's all I did. I said 0.19 can be converted to 19 over 100. 100 is a very nice square root that you can actually square root. And you end up getting the square root of 19 over 10. That is exact. That is our solution. How you doing? Okay? That's the exact value. Now we're assuming that this is an exact value too, not rounded. So if that's true, that's our exact value. What about tangent? Oh boy, here we go. How do we figure out tangent? Well, guess what, folks? We know what sine is and we know what cosine is. Tangent, theta, is equal to sine theta over cosine theta. Let's take sine theta and let's convert it into what? Let's convert it into a fraction. Yeah. So we're going to take 0.9 and we're going to convert it into a fraction. How do we write that as a fraction? What? Okay, 9 over 10. Good job, everybody. So that is equal to sine. That equals sine of theta. So what we're going to do is we're going to plug in this, we're going to plug in this, we're going to evaluate it, and we will solve. So we end up getting 9 over 10 equals square root 19 over 10, and we're going to evaluate it. What do we do when you have a fraction divided by a fraction? Flip and multiply. We get 9 over 10 times 10 over the square root of 19. Holy Moses, they cancel each other out. We get 9 over the square root of 19. Can we have an irrational number on the denominator? Let's rationalize it. Multiply it by the square root 19 on the top and the bottom. Doesn't turn out very nice, but you end up getting 9 square root 19 over 19. Make sense? It's kind of funky, right? It's kind of funky. It's kind of abstract, but has some problem-solving aspects that people dig. Okay? Here's another one. Oh, more examples. If theta is an acute angle, so we're talking about positive numbers here, positive numbers, such that cosine of theta equals 0.3, then find the following. Try it out. I'll give you a clue. It's supposed to be up in the corner. Use Pythagorean's identities. I need to stand up. My legs are atrophying.
Plug it in. So you would do sine squared plus cosine squared equals 1.
That's where you start. Start with Pythagorean's identity, that is sine squared plus cosine squared equals 1. Watch out. 0.3 squared is not 0.9. It's 0.09. Watch out. A lot of you are getting to the point where you're square rooting both sides as you convert it into a fraction. Don't forget to square root the top and square root the bottom. And don't worry about plus or minus because it's an acute angle. So square root, what's that equal to? 1 minus point. What's 1 minus point.
Oh.
How you doing? 10. That's correct. Oh, you guys are getting this better than I anticipated. Great. You smart cookies, you.
Did you say smart cookies?
Yeah, smart cookies. Sine squared plus cosine squared equals 1. We have sine squared theta plus 0.09 equals 1. We have sine squared theta equals 0.91. We have sine squared theta equals 91 over 100. We're going to square root both sides, and we get sine theta equals square root 91, which is prime, over 10. If you got that, arrivederci. Very nice job. That's how you speak Italian. You just say A's at the very end of everything.
And you gotta make your hand do this.
It's stereotypical, but still, if Subway can do it, Subway's new commercials drive me nuts. That's a good sandwich, Jimmy. That's a really good sandwich. And then, yeah, I know. You're done good. Like, give me a break. Who do you think we are? Give me a break. You know what? Forget about it. So, tangent. Tangent is sine theta over cosine theta. Oh my goodness. We have all the information we need, sorta. Cosine theta, what would that be as a 3 over 10? Hey, so we can actually plug it in.
You don't have to use fractions.
Yes. How would you do it without a fraction? You would do square root 91 over 10 divided by 0.3?
Find the decimal sign.
No, find that decimal. Puh. Square root 91, that's not going to give an exact answer. If it doesn't say use a calculator, if it doesn't say use a calculator, do not use a calculator. Calculators are only allowed when it says use a calculator. You got it? Good. Did you get 3 over 10?
I loved it. I got 3.18.
You got 3.18. That's not right. You know why? More decimal places, please. What'd you get? Keep going with your decimal. If you do it, you have to do. You could do it. I'll allow 13 decimal places, and then you can do it. Because I think your calculator only does 12.
Well, it depends on how big your number before the
I just don't want. I don't want it. Nobody wants that. We don't want that. We want
Is they try to do like
Exact
one-
we want exact values. Okay, this one turns out to be what? So it's square root of 91 over 3?
Yes.
Cool. Let's keep going. Secant. Ooh, cosecant, I mean. Luna, did you figure this one out? No? It's 1 over sine of theta. What was sine of theta?
Square root 91 over 10.
Square root 91 over 10. I guess we need to flip it
10 over
and evaluate. 10 over the square root of 91. What next? Rationalize that denominator, right? We get 10 square root 91 over 91. You got it? Good. Okay, that's exciting, right? You're getting it. So that's the beginning of identities. That's the very first thing that you come up with. And I find this to be a little bit more difficult, a little bit more tricky, but it's kind of fun. I like it. Anyway, this is great stuff right here. Now this is saying apply the 3 sets of identities. The reciprocals, the Pythagoreans, and the quotients. And try to get this side. They're going to ask you this. Use trigonometry to transform one side of the equation into the other. And so generally the rule is you take the complicated side and you turn it into the easy side, the uncomplicated side. Check it out. You're going to like this. I guarantee it. Secant theta times cosine theta equals 1. I am going to use the fact that secant theta equals 1 over cosine theta. That is a reciprocal identity. And I'm going to take this and I'm going to plug it in right here. 1 over cosine theta times cosine theta equals 1. What happens? The cosines cancel and we get 1 equals 1. We put a check mark to identify that we are finished. Isn't that nice? What? Mind blown. Here, look at this one. This one looks like it's a gnarly Charlie. This one's not very good. Yeah, it's gnarly. It's a gnarly Charlie. Okay? What do we do? Oh my goodness, yes.
Before we go on, I don't know what we just did.
We applied a identity from page 276 or right here. Slide 5. We applied the fact that secant equals 1 over cosine. Equals it. So if it equals it, we can substitute it in. So we went here and we said, hey, we're going to go ahead and, nope, wrong one. There we go. And we're going to say the fact that secant equals 1 over cosine, we're going to substitute it in for secant. And if we substitute it in for secant, it cancels it out.
So we're just,
Why did we cancel it out? What
We
did
want to prove
Oh,
that this equals 1. So we simplified the more complicated side, and we prove it equals 1.
your directions are
we just don't know why we need to find that it equals 1.
really because you're trying to set one
Because
side
you're
of the
trying to
equation
have
equal
it
to
so
the other.
that-
Okay.
You're trying to prove it.
Yeah.
Like,
Why would we need
You
to?
should just say for those instructions that have used trigonometric identities to transform one side of the equation to the other, just say prove it.
prove it. Well, I can't, because it's not a proof. But I can say, show it. Show that it does it. Show that it is equal to the other side.
but that's only for as many as 1, right? Like if that set equals to 2.
No, it could equal anything. You could create a wild one, and you can show that this gnarly little secant, cosecant, plus tangent, cotangent equals sine squared theta. And you show that the complicated side equals the simplified side. You have to prove it using, you have to I think proof would be okay. I think actually proof would be okay in this particular instance.
You can't be definitive.
Well, you can't be definitive on your stats. But, yeah. So you are providing evidence that that whole weird side, secant theta plus tangent theta times secant theta minus tangent theta equals 1. Show me that you can do that. Show me you can apply our identities to do that. This is all identity work. All identity work is for calculus. Okay? So, like I said, it gets into the theoretical realm, and we stop seeing angles, we stop seeing those things, we start seeing identities. Okay? Let's do this one. How do we do this one? We're going to apply as much background knowledge as we can. I am going to FOIL this. First, outside, inside, last. Secant times secant is what? Secant squared theta. Secant times negative tangent is negative secant theta tangent theta. Tangent theta times secant theta is positive secant theta times tangent theta. Ha! Ooh! What'd you say? It cancels itself out. Okay? We're getting there. Tangent times tangent, negative tangent, is negative tangent squared theta. And that needs to all equal 0. Now, just like Mr. Zuniga said, the middles cancel out.
I'm sorry, what?
Oh,
I don't think that was a proper use of movie quotes.
like Mr. Zuniga said, the middles cancel out.
He didn't actually say that, did he?
No,
You said that.
he was quoting him.
Luis Zuniga, the person sitting next to you, said that these will cancel out, and they cancel out, and we get secant. Okay, focus, please.
That's
This
Mr.
is awful
Miyagi,
now.
not Zuniga.
Okay, hold on. So now we have secant squared theta minus tangent squared theta. Let's go back to our Pythagorean identities to see if any of them are going to fit in. So what did we do here? We FOILed. Or distribution, or whatever you want to call it, okay? We're going to go back to our identities on page 6. Pay attention. And we're going to look to see if any of these fit. Now, sine, okay, we're not using sine, we're using tangent and secant. There's tangent, plus 1 equals secant. Wait, look at this. Secant squared theta minus tangent squared theta equals 1. So we are going to go over here, and we are going to say the Pythagorean identity.
So you can just say that, and then it's like, that's it? It's
Or
just-
what if you used the original one, the tangent squared tangent squared theta plus 1 is equal to secant squared
You would have to,
theta, and then you would just plug it in, and then you would have tangent squared theta minus secant theta.
you are right on the money. That is exactly the stuff that you're going to have to do later. Okay? She said, well, what if we're just going to plug in the fact that secant squared theta equals, is it 1 minus tangent squared?
Tangent squared theta plus 1.
Tangent squared theta plus 1. Tan squared theta plus 1. And we take the fact that that equals it, and we're going to substitute it in here. And when we substitute it in there, we get tangent squared theta plus 1 minus tangent squared theta equals 1, and our tangents cancel, and we get 1 equals 1. Yes, that is identities. That is the essence of identities. Plug it and get it. Oh, the recording. Oops. Plugging stuff in and getting stuff out. Wow, I did not mean to do that. Pardon my French. I will probably bleep that out. So also, these Pythagorean identities are on page 276. So you can also use your book to reference it. They are also in the very first page of your book. Hold on, listen. They're in the very first page of your book, or second page of your book, or third page of the book, whatever it is. It's in the front. There they are. It's in the front of the book. What I'll probably do is I'm going to copy that front page of the book. I'm going to put another large unit circle on the opposite side, give you a cardboard handout, and then you guys can work on that. Okay?
Cardboard handout.
Yes, cardboard, like paper, thick paperboard. Cardstock, yeah. Okay? So a couple of other things. Hold on. These are really quick. We could say true or false. Are these true or not? And you can use Pythagorean's identities, or you can use any identities to figure that out. Okay? For instance, is secant theta equal to 1 over cosecant theta? Well, let's convert some stuff. Okay? Let's convert some stuff. We can, and one of the big things is you can only work on one side at a time. Okay? Work on one side. The answer definitely is false. Okay? This is false. It says do the work to find out. Well, secant theta is equals to 1 over sine theta. And I know for a fact that secant theta does not equal sine theta. So this is false.
Is it sine theta? That's 1 over cosine. That one.
Secant is 1 over cosine. You could also say 1 over cosine does not equal sine. Some of the other questions I'll say is put everything in forms of sine and cosine. Okay?
Secant is 1 over cosine.
Secant is 1 over cosine. The same thing as 1 over cosine does not equal sine of theta. Sine of 45 equals 1. Well, that's the same thing as sine of pi over 4 equals 1. I know the fact that sine of pi over 4 does not equal 1. Why? Because sine of pi over 4 does equal square root 2 over 2. True or false? 2 pi over 3 radians is equal to 120 degrees. Well, I'm going to convert that into degrees and see if it's true. 2 pi over 3, the pi's on top, so I'm going to multiply it by the pi on the bottom and take 180. This was back from the previous section. Our pi's cancel. 3 goes into 180 60 times. 2 times 3 is 120. So 120 equals 120. That works out. This is true. This is false. Okay. How we doing? How far away are we? Oh, we're going to get... Oh, you know, you guys can probably do the homework. You guys could probably do the homework. There's going to be a question that's regarding these little notations, and I decided to actually give you the information about that. Okay? And I don't think this page number is right either, so cross that out. But anyway, this tells you how to do it. It's actually pretty straightforward. That's a huge... These are just angle of elevation, angle of depression. It's basically the angle up and the angle down. Okay? That's all it's saying. It's not too... It's just to premise questions. So, Elizabeth, I will answer all your questions Thursday.
It won't be here Thursday.
I will answer all your questions Thursday, and I'll record it. Okay, there's your homework. I want you to do this, and you have that little portion at the very end of your last homework to do. This is due Thursday. And if you guys get stuck on some of those problems about degrees and minutes and arc minutes, let me know. See you later, Michaela.
What? Thursday, we're taking the first.
And F10.